Welcome to our exploration of Terraforming Mars, preparing for climate challenges beyond Earth. In this video, we'll journey through the current environmental conditions on Mars and discuss why terraforming has become a crucial topic for humanity's future. From enhancing the Martian atmosphere and raising temperatures, to addressing radiation challenges and ethical implications, we'll uncover the multifaceted approach needed to transform our neighboring planet. Join us as we delve into the technological innovations and economic hurdles that could shape this ambitious endeavor. 1. Understanding Mars' current environment. Mars is a world of extremes. Its atmosphere, primarily composed of carbon dioxide, lacks the oxygen-rich air that we breathe on Earth. The stark difference in atmospheric composition is compounded by its low atmospheric pressure, which is less than 1% of Earth's. This results in a surface temperature averaging a frigid 63 degrees Celsius. Mars' thin atmosphere cannot support liquid water, a crucial element for life as we know it. Additionally, the planet's surface is bombarded by radiation due to the absence of a protective magnetic field. These harsh conditions present significant obstacles to human habitation. 2. The rationale for terraforming Mars. Why terraform Mars? The answer lies in humanity's quest for survival and exploration. Establishing a human presence on Mars could act as a safety net against potential Earthbound disasters. A self-sustaining colony on Mars would ensure the continuation of human civilization in the face of catastrophic events. Furthermore, the scientific and technological advancements gained from attempting to terraform Mars could have profound implications for our understanding of life and ecosystems. By transforming Mars, we not only secure a potential new home but also push the boundaries of human exploration. 3. Building up the atmosphere. A thicker atmosphere is essential for making Mars habitable. One proposed method is to introduce ammonia into the atmosphere. Ammonia, abundant in some asteroids and comets, could be redirected to Mars, where its impact would release nitrogen, a vital component for a breathable atmosphere. However, ammonia is unstable and breaks down quickly, posing a challenge for long-term atmospheric enhancement. Another idea is to use hydrocarbons like methane, which could enhance the greenhouse effect. Yet, these gases are light and could escape into space, making their use a temporary solution at best. 4. Raising the temperature. Warming Mars is crucial for creating conditions where liquid water can exist. One imaginative solution involves deploying massive orbital mirrors to reflect sunlight onto the Martian surface. These mirrors could raise temperatures enough to sublimate polar ice, contributing to a thicker atmosphere. Alternatively, the use of conductive nanorods made from Martian minerals has been proposed. These nanorods would absorb and scatter heat, warming the planet efficiently. However, both methods require substantial technological advancements and resources, highlighting the complexity of climate engineering on a planetary scale. 5. Introducing oxygen. A breathable atmosphere is impossible without oxygen. Electrolysis of water, splitting it into hydrogen and oxygen, is a potential solution. Recent discoveries of groundwater on Mars provide a source for this process. However, the energy required is immense, estimated at 7 zettawatt-hours to produce Earth-like oxygen levels. This energy could be supplied through advanced nuclear technologies. Yet, the stability of the generated oxygen in Mars' atmosphere is a matter of ongoing research, and the energy demands pose a significant hurdle. 6. Overcoming radiation challenges. Radiation poses a severe threat to any potential Martian inhabitants. Without a magnetic field, Mars is exposed to harmful solar and cosmic radiation. Solutions include creating artificial magnetic fields or constructing habitats underground. Lava tubes and subsurface bunkers could offer natural protection from radiation. These strategies leverage Mars' geological features, but the absence of a global magnetic field remains a significant challenge for long-term colonization efforts. 7. Ethical considerations in terraforming Mars. The ethics of terraforming Mars cannot be ignored. If life, even microbial, exists on Mars, our interference could lead to its extinction. This raises questions about our responsibility to preserve extraterrestrial life. Furthermore, some argue that Mars has its own intrinsic value and should remain untouched. Altering its environment for human benefit could be seen as a violation of planetary preservation principles. The ethical implications of terraforming extend beyond Mars, challenging us to consider our role in altering other worlds. 8. Economic challenges of terraforming Mars. Terraforming Mars is not only a scientific challenge but an economic one. The costs, potentially in the trillions of dollars, raise questions about funding and resource allocation. Diverting resources to Mars could mean less investment in pressing earthly issues like poverty and environmental conservation. Additionally, creating a self-sustaining economy on Mars is a complex task. Innovative solutions are required to develop industries and trade systems that can thrive in the Martian environment. The economic feasibility of terraforming is a critical factor in its pursuit. 9. Technological innovations and feasibility. The quest to terraform Mars drives technological innovation. Atmospheric engineering, magnetic field generation, and biological adaptation are key areas of focus. Technologies like orbital mirrors and engineered microorganisms hold promise but are still in their infancy. The timeline for developing these technologies spans decades, highlighting the long-term nature of terraforming projects. While theoretically plausible, these innovations require extensive research and testing to assess their practicality.